Hello and welcome back. Today we are going to be looking at some radicals, how to simplify them and work with them a little bit. So we're going to start with, we're going to start with square roots because those are going to be the ones you see most commonly. Although we will talk about radicals that aren't just square roots. So whenever you have a number inside of a radical, there are actually ways to simplify it or figure out what the value is without just knowing it off the top of your head. Typically, you factor the number inside and you pull out sets to the outside so that you can multiply. So I, I know I just said a bunch of big math words, and now I'm going to switch over to the board so that I can actually show you what I'm talking about. So let's say we start off with, let's say, the square root of 25. Now, some of you already know this is 5, but you might not know why it's 5. On every square root, there is a power written right over here in this space. Now, for square roots, it tends to not be written. Kind of like, you know how you can always multiply by 1? This is one of those things where it's just kind of understood to be there. But in there, if you don't see it, you assume there's a little 2 there. So what this 2 means is that you need to multiply that many of that number in order to bring it to the outside. So what I mean by that is, so let's say, first and foremost, let's clarify something. So 25 equals 5 times 5. I think that's not a controversial statement. It's pretty straightforward. So what we're going to do is we are going to rewrite this square root as, instead of being the square root of 25, we are going to write the square root of 5 times 5. Now, interesting thing about this square root, it is specifically looking for sets of 2. And now we have a set of 2 5s. So what this means is that we can grab these 5s on the inside and pull them out as one set of 5s. So that 5 gets to move outside of the radical. And if there's nothing else there, we assume there's a 1. But the square root of 1 is 1, and multiplying by 1 is not a big deal. So basically, we pulled everything out of the radical. There's nothing left. Now the 5 is just on the outside, which means that we have just proven that the square root of 25 is 5, because there were 2 5s in there. And according to the way a radical works, if they're all multiplied, you can just pull out that number whenever you have the correct number of them for a set. So to give this a second example, one that, might be a little bit bigger, let's say we're doing a different kind of radical. Let's say we're doing a different kind of root. Let's say we've got the cube root of, no, not 8. Let's do the cube root of 16. Okay, so 16, we can factor that. Okay, so 16 is 4 times 4. I think that's fair to say, but that's not enough for 3. And when we're dividing a number, we can't really get 3 of any given number because, when we divide, we just get the 2 of them. So that's no good. So instead of doing that, what we're going to do is we're going to factor 16 into its prime factors. So we're going to do a prime factor. So that means we're going to factor 16, and we're going to factor all of the numbers that come with it until we hit prime numbers. If we hit a prime number, we're going to underline it. That means we'll stop there. So as we just said, 16 can be divided by 4 and 4. Now, 4 is not a prime number, so I can divide 4 by something. So let's divide by 2. So 4 can be divided by 2, and all of these 2's are prime. So all of them are prime numbers, which means if I multiplied them all together, I would get 16. So that means that I can rewrite 16 as just all of those prime numbers. So let's write them all out. So we got 2 times 2 times 2 times 2. Boop, boop, boop. So now I definitely have a set of 2s. So I can pull that set of 2s to the outside of my radical. However, there's one 2. Poor guy. He's all alone. He has to stay inside the radical by himself because he was not pulled outside. And now, because we can't factor that 2 anymore, this would be our final simplified answer. So if we needed to simplify the cube root of 16, we would just factor it and then get the number here. Now, I will do one more big example. because I know that sometimes, so sometimes when you're working through stuff, you just have weird examples, and sometimes you just need to go through them. So let's say, ooh, goodness me, that wasn't very pretty. So let's say we want to do the square root of 100. Now, I know what some of you are thinking. Some of you are thinking, hey, wait a minute, 100 is just 10 times 10. So if we do that, we'll pull it out right away. And you are correct. That would be one way to do the square root of 10. But let's say you don't remember that off the top of your head. Let's say that you're like, wait a second, I don't know what times itself is 100. How else can I do this? Well, the easiest way to start would be to say, 100 is an even number. It ends in a 0. So since it ends in a 0, that means I can divide it by 2, and you'd be exactly right. So 100 divided by 2 is 50. So 2 is prime, so I can stop there on 2. But I can keep going with the 50. So 50 is, let's say it's 2 times 25. So you go, okay, so 2 is prime. Wait a second, I know what 25 is. We did that earlier. That's 5 times 5, and you are exactly right. So now what we have is we have 2 times 2 times 5 times 5. So now there's actually multiple pairs that we can pull out of the radical. So everything's coming outside of the radical. The 2 comes out, 5 comes out. But wait a second, how are these put together? Well, we were multiplying them before, so we will continue to multiply them after they're outside of the radical. And oh, would you look at that? 2 times 5, that would be 10. Which means that the square root of 100 is 10, something we know to be true. So if ever we have, a radical that we need to deal with, we'll make sure we know what the number is, and then we'll do some prime factorization, pull out some sets, and if we get more than one number in any particular spot, we'll just multiply those. So just to give one last little bit of an example. So if we were to say have 2 times 3 square root of 3 times 5, because, we pulled out a pair of 3s, pulled out a pair of 2s, but there's 3 and a 5 left over, that would be the same as saying 6 square root of 15. Because 3 times 5 is 15, and because 2 times 3 is 6. The ones on the outside stay on the outside, the ones on the inside stay on the inside. Very, very straightforward. So, with all of that in mind, now let's head back to the presentation and see what's next. Okay, so now we're going to talk about variables for a second with our radicals. So if there are variables in the radical, we're basically going to do the same trick, except it's going to look a little different. So let's go back. And now we're back from outer space. Sorry, I like singing. Every now and then I do that. So let's say we have the third root of 16 times x to the 7th. Okay, well, we already know that the 16 is 2 times 2 times 2 times 2. So basically it's 2 to the third times 2 to the first. So when we get the third power, so this is a group of 3 2s, so that goes to the outside, so the 2's on the outside. And the other 2 is just left in there all alone by himself. So now you might see where I'm going with this. We can do the same with the x's basically. So we know that if we have a power of 3, we can pull that out, we can get rid of it. So that means we can do x to the third times x to the third times x to the first, because 3 plus 3 is 6, plus 1 is 7. So hey, would you look at that? So now we've got x to the third, x to the third, and x to the first. So this x is going to stay on the inside. He's all by himself. But these guys are in sets of 3. So I get to pull those guys out. So I have 2 of them. So that's x times x, which means our final answer would be 2x squared, because x times x is x squared, square root of 2x. So that cancel. Oh, wait. Cube root. My bad. Cube root. This should be a 3, brain. Come on. Anyway, so cube root of 2x. So, all right, cool. So that means that if we have a power, we just figure out how many sets there are. Now, there's actually a faster way to do this, and I shall demonstrate it for you now. So let's say we get something crazy. Let's say someone throws big numbers at us because, I don't know, they might be trying to teach us something, and so they want us to know how it works really well. So let's say we have 7th root of x to the 38. Now, oh my goodness, I don't know about you. I really don't want to separate this. This is too much work. So let's say we got 38 here and 7 there. Okay, fair enough. So that means every set of 7 inside of our 38 goes to the outside, right? Right. So now, if we just do this division, the answer will be the number of sets. The remainder will be what's on the inside. So let's run through this. So how many times does 7 go into 3? It doesn't, so there's a 0 there. And then 7 times 5, that would be 35. And we're left with 3. Okay, so on the inside, we should have 7 or x to the 3rd power, because there's 3 of them left over. And on the outside, we should have x to the 5th. So sets on outside, so x to the 5th, and remainder on the inside. So that's x to the 3rd, root 7. And this would be our answer. Right there. That was fast. That was nice and quick and easy. So this is how we want to do simplifying radicals whenever there's variables involved. We'll just use their powers to make things a lot easier. So remember, inside divided by outside. The answer tells you what's on the outside, while the remainder tells you what's on the inside. And I'll go ahead and do one more example so you guys have plenty of examples to work with. Okay. So So let's go ahead and do just one more. So just one more of these before we move on. So let's say we have x to the 4th. And then we've got x to the 11th, y to the 12th, z to the 13th. Because, yeah, we can do more. We can do more than one at a time. So let's do x first. So 11 divided by 4. So that would be 2. 2 minus... 2 times 4 is 8, so minus 8. That's 3. So we have 2 on the outside, 3 on the inside. So that'll give us x squared on the outside. And with the 4th root, we have x to the 3rd on the inside. Okay, so now we go for the y's. So 12 divided by 4. Well, that's just 3. So minus 12, that's 0. So there will be no y's on the inside. So 0 y's on the inside, 3 y's on the outside. So on the outside, we will have y to the 3rd. And on the inside, we have no y's because it divided evenly. And last but not least, we got z over here. Good old z. So we got 13 divided by, still 4, because you always divide by the number on the outside. That's very important. And so 4 goes into 13 3 times. So minus 12. Boo boo. We got a 1. So on the outside, we have z to the 3rd. But on the inside, we have z to the 1st. There we go. All taken care of. Complete final answer. You know, you can go to Double Jeopardy with this. Beautiful. Great. Awesome. So with that, we can cut back over to the presentation and check out what's next. Okay, so next up, writing them as fraction powers. Okay, so you noticed how we were doing the division over there already. Sometimes that gets annoying. Sometimes that gets really annoying, having to write out all the division all the time. That can be very lengthy, very time-consuming. So there's actually a faster way to do it. So let's go back to the drawing board. And let's do this, but this time let's do it a little bit faster, a little bit easier. So, let's do white. So gotta get the marker. Okay, so let's say we have 4th power, and let's say we have x to the 11th, y to the 12th, and z to the 13th again. Okay, so this time, what we're gonna do is we're gonna write these as fractions. Okay, we're going to write every single one of these as a fraction. So every single one of these guys is going to have a fraction for their power. He said he would write y, but he wrote x. Is he being silly? Yes, I am being a little silly. Sorry about that. So the number on the outside is always the denominator. So the denominator for all of these guys is going to be 4 because they're all inside of the fourth root. And that's fine. But for each one, their individual powers are going to be, or their individual numerators, the number on top is going to be whatever number was on top on the inside. So, like before, we're still dividing them by 4. It's just now we're rewriting it, so it's a little bit easier to do that. So we have x to the 11 over 4 times y to the, so 12 divided by 4 is 3, so we can go ahead and put a 3, times z to the 13 over 4. And this would be our final answer because we can't really simplify the x's and z's much more than that. If you want to, you could separate them out. So like, let's say we had, so 11 is the same as 8 plus 3. So we could have x to the 8 over 4 times x to the 3 over 4. And that would be the same as x squared times x to the 3/4. But you see how that's making more work for ourselves? You see how we're having to write more in order to do that? Yeah, typically we don't want to do that. So typically, once we get it into a fraction power, we'll just leave it like that. If there's more power shenanigans we need to do after the fact, we can try that later. For right now, this is perfectly fine. So with that in mind, we're going to cut back to over here. And I think all that's left is the, yeah. So now we got the TV time stuff. So in any case, I'm going to leave that stuff to you guys. And of course, we'll do them together in the synchronous hours. And next up, we're going to have logarithms and exponents. Yes, I really do love logarithms. I know a lot of people don't like them because they're a lot like exponents, but how do I put this? Some instructors don't always explain exactly how a logarithm works because you don't strictly need to know it in order to work with it, but I find that knowing it helps a lot. It makes the work a lot easier. But anyway, for now, we're good, and I will see you in the next video.